The reality is that you typically collect your own data. So you have a vector of data in Excel or in R. And if you're going to run a t-test, you're going to use a stats program to do that. Does R have a t-test function in there? You bet. Function is t.test. So how do we run it? Well, we just use the function t.test, and we pass it a vector, our hypothesized mean, mu, and specify our alternative being either two-sided for two-tail test, less or greater. So for this example, what I want you to do is to run this code in R. So pause the video, open up RStudio, get your Markdown document ready, and run this code. Alright, here's my R Markdown. I have it set up so that I'm going to set my seed, create my data vector. Now, just as a review, why did we set the seed again? Yeah, we're setting the seed so that we get the same data vector, same point vector of random points. For our data vec, we're going to create a sample size of 18 drawn from a normal distribution that has a mean of 33 and a standard deviation of 2.22, and then we're going to round to the hundreds place and save it as data vec. I also have mosquito fish. We're going to be working with this a little bit later. Our standard function is t.test. So t.test, and then we're going to pass it a vector. So for us, our demonstration is data vec. And then we're going to specify our mu. In the presentation, I asked, does data vec has a mean of 31? So we're testing if mu is equal to 31. Now, what are our hypotheses? Well, our null hypothesis is that the sample mean equals 31. Our alternate is that our sample mean is not equal to 31. So we're doing a two-sided test. Now the default is always two-sided. So we could leave it out, but I'll put it here just so you can see it. Once I run it, I get this output. This is the output that we need to write our conclusion or summary, because it gives us what test we ran, it's a t-test, gives us our test statistic, t, gives us the degrees of freedom, 17, and it gives us our p-value. So our p-value is less than 0.05, which means we reject our null hypothesis and conclude that our sample mean is not equal to 31. There's a couple other things that I want to point out here. One is this. So the t.test function will tell you what the mean of our vector is. So it's comparing. Is this mean equal to this mean? Yes or no? In this case, it's not. The other thing that it does is generates a 95% confidence interval. This interval is the same interval that we would have calculated if we did it by hand. And we could use it if our assumptions are met. So if all of our assumptions are met and our confidence interval does not capture our hypothesized mean, then we should get a significant test, meaning a p-value less than 0.05. So that's what this output is saying. We've got our hypotheses, we get the same output, and now what's our write-up? Our write-up is that our data vec does not have a mean of 31. We ran a t-test, our t observed is 2.97, degrees of freedom is 17, and our p-value is less than 0.09. We hit all 5 items of interest. Now, we didn't have to calculate t observed ourselves. R does that for us. We didn't have to generate a critical value or manually use the pt function to get a p-value. R does that for us. So when we have a vector of data, it's very easy to do a t-test. Alright, so I've posted mosquitofish.csv. This is a data set that has 4 variables in it. The first 3 have a sample size of 200. The last one has a sample size of 25. The idea is that we measured mosquito fish from 4 ponds, and now we're going to compare the means for those 4 ponds. So what I want you to do is read in the mosquito fish and then run t-tests to answer these 4 questions. So for pond 1, is the mean equal to 24.5? For pond 2, is the mean equal to 25.15? For pond 3, is the mean smaller than 25.05? And for pond 4, is the mean greater than 23.75? Note, these are two-tailed tests because we didn't specify direction, but these are one-tailed tests. So pause the video, import Mosquitofish, and try to run t-tests for each of these 4 variables. Alright, so hopefully you had a very easy time doing this. If not, let's review it. Alright, so here's my code. Pond 1, I'm using t.test, and what we want to do is use pond 1. Well, if we note up here, I've got my vector, or my data set is Mosquitofish, and then I have pond 1, pond 2, pond 3, pond 4, and so forth. So I'm testing pond 1. It's in a data frame. We're going to use Mosquitofish $pond1. We're testing against the mu of 24.5 because we're asking if it's equal to it, or it's a two-side test. So we're going to use two-sided, and I'm going to leave it off because that's the default, is to run a two-sided test, and I get my output. So I have everything here that I need to make my write-up, and the write-up has to include all 5 things. So what we do is look at our p-value. If it's greater than 0.05, then we fail to reject our null hypothesis, which means our means are equal. If the p-value is less than 0.05, then we reject our hypothesis and conclude that the means are not equal. So here it's less than 0.05. We conclude that our means are not equal. So our write-up goes back to the biological question. So average size is not equal to 24.50. We ran a t-test. Our t-observed value is 3.25. Our degrees of freedom is 199. And our p-value is less than 0.001. So that's pond 2. I'm sorry, pond 1. Pond 2 asks, is the mean equal to 25.15? So again, here's our vector. I use the data $ vector. I specified our mu, what we're testing against. Our alternative is two-sided. It's two-sided test, two-tailed test. So I'm going to leave that there. And then I run it, and now we need our write-up. So our write-up goes back to our p-value. In this case, our p-value is greater than 0.05, so we would conclude that average size is equal to 25.15. We ran a t-test. Our t-observed is negative 1.83. Make sure the negative's in there. For our p-value, our degrees of freedom, we need a subscript. So 199, I'll use brackets here just to try to represent a subscript, but we can write it as df equals 199 or as a subscript to our t. Either way will be okay. And then our p-value will be less than 0.07. And that's our write-up. For pond 3, we ask, is the mean smaller than 25.05? So again, it's still the vector. We specify our mu, 25.05, but now we specify a direction, so it's a one-tailed test. In our question, we are asking if our mean is smaller than this, so our alternative is that x bar is less than mu. Thus, alternative equals less. When we run it, we get this output. Nothing changes with our interpretation. We still look at our p-value. Our null hypothesis is that the means are equal. We failed to reject that, so therefore our average size is equal to 25.05, or we can go back to our question, is the mean smaller than 25.05? No. The average is not smaller than 25.05. We ran a t-test. T observed is negative 1.25. Degrees of freedom is 199. P-value is less than 0.11. And lastly, pond 4, is the mean greater than 23.75? Thing that changes is alternative. We specify greater because we're saying x bar is greater than the mu. We've updated our vector and our mu, and we get this. So our p-value is less than 0.02552. So we reject our null hypothesis and conclude that the mean is greater than 23.75. And again, t-test, t observed is equal to 2.05. Degrees of freedom in this case is 24 because it's smaller sample size, and our p-value is less than 0.03. So this is our write-up. This is how to do it in R. Now, one thing we didn't address were the assumptions. We didn't address these assumptions when we did stuff by hand because you can't really check your assumption of normality by hand. We can only do it in R. So when you have a vector of data that you can run a t-test on, well, you should check your assumptions. Our assumptions are that the data are random and independent. This is usually determined by how we set up our data or how we set up our experiment. In this class, everything that I give you will be random and independent, and I'll state it as such in our problem. The second assumption is that our data are normally distributed. Why? Why do we make this assumption? Well, if our data are normally distributed, then this transformation will approximate a t-distribution. If we're not normally distributed, then this transformation will not approximate a t-distribution at all. And if we don't follow a t-distribution, then our p-value is going to be wrong. Now, fortunately, as our sample size increases, our t-observes will approach normality. So if we have a sample vector of 10,000, yeah, it's probably not going to be a huge deal that we're completely non-normal because our t's going to be, our t observed will approximate the actual t distribution. However, with the tools that we have in R, I don't think we should ignore that assumption. If we violate normality, we have options that we can run that address it. So here's an example. Let's say we have a skewed sample of data and we generate and we're testing a mean. Well, we're testing if our mean is equal to some value. It assumes that we're normally distributed. If I generate a bunch of random samples and calculate these t's, then this is our histogram of our t distributions. This blue line represents the actual t distribution based on the degrees of freedom that we have. And what you can see is that not only was our underlying data skewed, but we're actually a little bit skewed too with our t observed value. So we have more t observed on this side, so the middle of the bars to the left of the line, and we have fewer t observed on this side. So again, the middle of the bars to the left of our line. So we're actually shifted. Now, if this is the shift of our t observed, but we're using the blue line to figure out the p-value, so that's the area under the curve, don't you think the p-values are going to be wrong? Yep, of course they will be. So, before we can run a t-test, one of the first things we're going to have to do is to check our assumption. Now, that is first assumption, are data random and independent. I'll tell you, data are random and independent, but we can check normality. So how do we do it? Well, this is a review. Remember, we have two graphical methods, and we have a statistical method. So of the two graphical methods, we can do histograms with a normal curve. The strengths of this is that it's quick and easy. We can make a histogram, then we overlay the curve, and this normally shows us some skew. It can show us kurtosis. Definitely shows us outliers, especially if we have a couple of values that are really extreme. And if our data exhibit two peaks, the histogram really shows us, and it shows it very, very clearly that we have these two peaks. But all of this stuff really only applies to a large sample size. If we have less than 30 data points, it's kind of hard to adequately assess normality using histograms and normal curves. So here's the example of what I'm talking about. So we do our histogram of our vector we specify the breaks, make sure we have frequency equals false, and then you use curve with add equals t, and the curve, we're going to replace v with one of these. For us, it's the d norm. We've already talked about how to do this, so you can go back to those presentations, those homework assignments, and even the exam to see how to do it. For pond 1, this would be our histogram with the overlay curve. Here's the code. So we look at this and ask, is the pond normal or non-normal? Well, kind of follows it. We've got some high values here, but maybe that's okay. As I said, it's histograms. We try to assess our normality, and it's kind of tough to do. But we do see that we don't have any multi-peaks here. It looks like we only have a single peak. Better option, and actually the option that I recommend, is to do the quantile plots. Remember, this plots the actual quantiles versus quantiles that are predicted if we actually follow a normal distribution. If we're normal, all of our points will fall on a straight line, a straight one-to-one line. If we're non-normal, then it won't fall on the line. And it's difficult when we have small sample sizes, but that's why we're going to use the QQ plot function that's in the CAR package. We're going to use this because it adds a 95% confidence envelopes to that graph. If our points fall outside of that envelope, then and it's a large number of points, then we can conclude that the data are non-normal. Strengths of this is that it's easy to perform and interpret. We're looking for points that fall outside of that dash bar. But weakness is that there's no p-value to report. So if a reviewer really wants a p-value, quantile plots won't work. So just as a review, here's pond 1. Everything looks pretty good. Yes, we have a couple points that fall outside, but these are the extreme values, and as I said, those are okay. So if we were going to do a write-up, which we will be doing with QQ plots, I would state that a quantile plot suggests that fish lengths from pond 1 are normally distributed. If we do need a p-value, then we can run a Shapiro-Wilks test. This compares observed data to theoretical normal data. Our test statistic is a W, and that's kind of a measure of the difference. We run this test by using Shapiro.test and give it a vector. The strengths is that it does give us a p-value, but I think the weaknesses far outweigh the strengths, and the weakness is related to sample size. So if we have small sample sizes, basically anything less than 100, it's going to be tough to detect non-normality. We have to really be non-normal in order to detect non-normality as our sample size decline. And then for large samples, we're going to detect very slight deviations. So these are going to be some of these slight deviations will be the ones that we look at a QQ plot and we say, yeah, nah, everything's inside our lines, we're good. And normally, with these slight deviations, we can ignore them. Our tests are going to be robust against some of these assumptions. So my recommendation is always to avoid this test unless a reviewer asks for it. So just as an example, here's our Shapiro test for pond 1. Here's our output. As we're talking about reporting data, we're going to report our conclusion, our test, the test statistic, and p-value. And in this case, we don't have degrees of freedom. So for a write-up, we can say the lengths in pond 1 are normally distributed, Shapiro-Wilks test, W is 0.987, p-value is less than 0.07. Recall, this is the one time that I recommend that you can go to 3 decimal places for a test statistic. Alright, so we're going to just test normality for practice. We're going to rely on the quantile plots to assess normality. But if you want, you can do histograms with normal curves and Shapiro-Wilks test just for practice. From this point on, I'm only going to do the quantile plots. So pause the video and determine if pond 2, pond 3, and pond 4 data are normally distributed. I'll note pond 4 has missing data, so it has NAs. So if you get an error, you may want to go back and think about how you might be able to remove missing data before you generate your quantile plots. Alright, here's my R. we're using quantile plots, so we need to load the car package. So the car package is loaded, but just so you know, at the top, I do add a library section where I load the library so that if I knit the document, it's already here. So going back down, we want to run a quantile plot of pond1. There are vectors in a data frame, so we will use data $variable. I look at this. Everything looks pretty good, so our write-up could be quantile plots suggest lengths of pond1 are normally distributed. And that's it. We don't have a p-value to report, degrees of freedom, test statistic, or anything. It's just the test and the conclusion. Or I should say, the assessment. So pond2, same thing, QQ plots. Pond2, again, everything looks pretty good. I would say, again, quantile plots. Suggest that lengths in pond2 are normally distributed. That's it. I'm going to copy that just in case. So pond3. This one looks like there might be some curvature, but all of our points fall inside of our envelope. And remember, we need the middle of the point to fall outside, not just the edge. So everything looks good. So again, quantile plot suggests that lengths in pond3 are normally distributed. Now we get to pond4. So QQ plots of pond4. I run it. It works. I didn't have to do anything for it, for the QQ plots. So smaller sample size. Yes, we have a point outside there and a point out there, but I don't see any general pattern. And since this is kind of close to the end, I think I'm going to be okay with it, especially with a sample size of 25. So quantile plots in length in pond4 are normally distributed. Alright, so it looks like all of our data are normally distributed, which means we can continue with our t-test. So just as a quick review, to check this assumption, my recommendation is always to do the QQ plot. Use that for checking normality. Yes, in reality, when I look at my data, I always do a histogram first too. That kind of gives me a way to check to see if I inputted my data correctly. If I didn't, if I may have missed a decimal point, I'm going to see a bar that's really far away. But for the assessment of normality, use the QQ plots. Alright, so we've already checked our assumptions. It looks like all of our assumptions are met, but the question is, if we did violate one of our assumptions, if we did violate this normality, what would have happened to our t-test that we had just run previously? Could we trust that? Well, probably not. If we violate our assumption, then our t-observed value no longer follows that t-distribution, which means our p-value is going to be wrong. So if we violate normality, what can we do? Well, we really have two options. So option one is to perform a non-parametric test. A non-parametric test is called a non-parametric test because it doesn't make any assumptions about normality. These tests have less power than the t-test because we're going to throw out some of the magnitude data in our measurements. So when we run our test, we might not be able to detect differences. Of these two non-parametric tests available to us, we're going to run the sign test. So the sign test doesn't actually ask if the means are different. Rather, the sign test assess if the median of a sample equals some hypothesized value. So it doesn't compare the mean. The sign test is preferred because the only assumption of the sign test is that the two assumptions of the of this sign test is that our data are random and independent, as most of our tests are, and our sample size has to be greater than 5. So sign test is going to be one of our choices. Wilcoxon sign rank test is another test that we could have run. Unfortunately, this requires symmetry around the median. And this isn't, I'm not talking about 50% of the points below the median or 50% of points above the median. What I'm talking about is it takes the median. We have to be symmetric in terms of the magnitude of values. So if our median is 10, then our smallest value can be 5 and our largest value can be 15. And we have to have symmetry around that value of 10 based on the actual values. Normally, if we violate this normality assumption, it's because we're skewed, which by definition means that we're not symmetric around that median. So if we violate normality because we're skewed, then by definition we violate the assumption of the Wilcoxon sign rank test. So because of that, I don't think it's worthwhile to even introduce you to this test or even show you how to run it. We're going to learn how to run the sign test. Now, the downside is that the sign test tests the median. If we're interested in testing the means, then what we're going to do is do some form of bootstrapping. So these are randomization methods. Our options are to generate a bootstrap 95% confidence interval. We've already done this. You have the code for it. This is very easy to calculate and interpret. So basically, if our confidence interval captures our hypothesized mean, then our sample mean is not different from that hypothesized mean. If our confidence interval does not capture the hypothesized mean, then our sample means are different. This is going to be the one that we do. The other bootstrapping option is to do a bootstrap t-test. Now again, this only assumes random and independent data, because what we're going to do is to generate a bootstrap sample, bootstrap t samples, to generate our null distribution, and then compare our observed to the new null distribution. The problem with this bootstrap t-test is that we have to transform our data so that our null hypothesis is true. So we have to add or subtract terms and then divide by terms in order to get our actual sample population to match our predicted, our sample data to actually match our population data, or what we hypothesize to be our hypothesized data. If we do a bootstrap t-test and compare the results to a bootstrap 95% confidence interval, we get the same thing. Our conclusions will remain the same. So because of the extra steps to do the bootstrap t-test, my recommendation is don't do it. And we won't do it. We'll take the easier route and do our bootstrap confidence intervals and go from there. The sign test is a nonparametric test that will compare a median to some value. Note, again, we are not comparing the mean, rather we are comparing medians. What this test will do is to convert our values from the actual raw numbers to plus, minuses, and zeros. And then we'll do something called a binomial test with this. We'll cover a binomial test later as part of our categorical variable discussion, but know that even though we're going to use our binomial test, we are actually performing the sign test. So our data assumes, or the test assumes that our data are random and independent, and in order to find significance, we need at least a sample size of 5. This is going to be a sample size of plus and minuses that is equal to 5. Our hypothesis of the binomial test is this, where our proportions, we assume we have an equal number of pluses as minuses, or we don't have an equal number, but in reality, again, because this is a sign test, we're testing if our median equals to some value. So how does this actually work? Well, let's take a detour and let me see if I could explain it with pen and paper. Alright, so our sign test is testing if our median is equal to some value. Our null hypothesis is that it is equal to this value. Our alternate is that it's not equal to this value. So to demonstrate what the sign test is actually doing, let's consider this example. We have a data set with all of these numbers, 3, 4, 4, 5, 5, 5, 6, 6, 8, 11, 18, and 25. Hopefully you can see from this data set that it looks like we're skewed. We're skewed right because we have a couple of values that really spread out and are larger. In this data set, let's ask the question, is the median equal to 5? So our hypotheses, statistical hypothesis that we'll test is the median's either equal to 5, that's our null, or the median's not equal to 5. Well, what the sign test is going to do is going to look at each of these values and assign either a plus, a minus, or a 0. It's assigned a plus if our value is greater than the median. It'll assign a negative if it's less than our median, and if it's equal to the median, then it gets assigned a 0. So 3 is less than 5, so that's a negative. 4s are negatives. 5s are zeros. And then everything after is a plus. Now, if our actual median is equal to 5, then we expect half of the data points to fall to the left of it, half of the data points to fall to the right of it. So we can test this using a binomial test, which actually tests proportions. So if we actually had the median, we'd expect exactly half of the pluses. We'd expect half pluses and half minuses. What we can do is test how likely it is to get 6 pluses if the probability of having a plus is actually equal to 50%. So for the sign test, we would ask, what's the probability that we could get 6 successes or more if the probability of success is equal to 0.5. Alright, so what we can do is actually calculate this, because we can say, well, what's the probability of getting 6 successes? What's the probability of getting 7 successes? What's the probability of getting 8 successes? And what's the probability of getting 9 successes? Now, we have more than 9 data points, but we only include the counts that are pluses or minuses, so in this case it's 9. We figure out those probabilities, and since our null hypothesis assumes that our value is the median and that we should have half the values above and half the values below, our binomial distribution is symmetric. So we can multiply the sum of those probabilities by 2 to get the second tail, the lower tail of this. We can do this by hand, or we can do it in R. Are we going to do this stuff by hand? No. We'll actually use R to do this. So let's go talk about how to do this in R. So as I said, we can do the binomial test in R. It's the binom.test, where we give the number of successes, total sample size, the probability of success, and state whether we're doing two-tail or one-tail test. But we're not going to run this because I have a general script for the sign test. So with the sign test, what it'll do is take our data vector, usually data $ variable format. We're going to save that as a vector. We're going to specify our hypothesized value that we're testing against, and then it goes through a series where it figures out how many values exceed our hypothesized value and saves it. It figures out how many of our values are less than the hypothesized value and saves it. Figures out how many total values we have, again excluding all of the ones that equal our hypothesized value. And then what it does is it takes the smaller of those two values and passes it on to this binom test so that we can generate a p-value that we would then report. I do say note, may need to revise smallest line if doing a one-tail test. For this class, we will always just do a two-tail test. After we learn how to do this, I will actually give you a function that runs the sign test for us and does now allow a one-tail test. So let's return to our example and show you how I would pass this example to the sign test. So here we are in RStudio. I took that data example and created a vector called dat. It's the same numbers that we did when we calculated it, when I was showing you what the sign test is actually doing. I then copied and pasted this code that was in the presentation. This code. and pasted it into RStudio. I then replaced this line to represent our data vector and replaced the second line to say that our hypothesized value is 5. I left everything else the same. Now, I run it and I get this output. Now, this output says that we're running a binomial test, but we know, based on what we're doing here, this positives, negatives, and total, that we are actually doing the sign test. What we want to look at is the p-value here. That's what we're interested in. P-value is greater than 5, so it goes back to our write-up, to the conclusion, to the initial question. Was the median equal to 5? Yes, the median is equal to 5. Sign test, that's what we ran, and our p-value is equal to 0.51. 0.51. We don't have a test statistic. We don't have degrees of freedom because the sign test doesn't have that. It's a more exact test. So hopefully you can see it's not terribly difficult. It's just copy and paste our code for the sign test and replace 2 parts of our script. As another example, let's consider pond 1. So in pond 1 we asked, was the mean equal to 24.5? Let's ask the other one. Is the median equal to 24.5 so that we can use the sign test? I did the same thing. I copied and pasted right into R. I updated this mosquito fish $pond1, so I updated the first line. I specified our hypothesized value at 24.5, and I left everything else the same. And when I run it, I get a p-value of 0.0004994. So we can do our write-up as the median of pond 1 does not equal 24.50. Sign test p less than 0.005. I will note that this video has the correct code. The presentation that's on Blackboard may be incorrect. So it may have these signs as pointing the same way. We actually need them opposite directions. So you can make a note of that. If you take this code, copy it, and put it into your useful function scripts, then you will always have the correct code. Alright, so now just for practice, let's do the sign test for these next 3 ponds. Again, I changed the values, but these are the same values that we tested against the mean. And once you do the sign test, I want you to go back to look at the t-test and see if any of the conclusions derived from the t-test differed from the conclusions derived from the sign test. And if they are different, come up with an answer as to why they may be different. So here's my R Markdown document. Here's my pond 1. We get the same numbers, same answers. So for pond 2, we ask, is the median equal to 25.15? I copy and pasted my script, changed this line to mosquito fish $pond2, changed my height val line to 25.15, and when we run it, we get this output. We only want the p-value, which is greater than 0.05, and thus our median equals 25.15. For pond 3, same thing. Copy and paste the script, updated that line, updated this line. I run it. I get a p-value of 0.62, well over the 0.05 cutoff, so our median equals 25.05. Pond 4, is the median equal to 23.75? If we run it, we get a problem. And we look at this output. X must be non-negative and integer. What that essentially means is that we can't have missing values. So for pond 4, we had missing values here. One way we can get around it is to issue the na-omit command prior to saving it as a vector. Once we do this, this will strip out all of the missing data and only pass that vector of 25 values. Now when we run it, it'll work. And we get a p-value, 0.043. So once we remove our missing values, we can conclude the median is not equal to 23.75. We ran our sign test, p-value 0.04. I will note that the presentation said larger for pond 4 and smaller for pond 3, but again, I'm only going to do are they equal, because trying to adjust this script to do a one-tail test is a little bit harder. We have to do things manually. Once we have the script, once I give you the function, you'll be able to do larger and smaller or equal. So that's a sign test. Pretty easy to run. It tests the median and not the mean. And as if you did your comparison, you will see that the results of the sign test match the results of the t-test. Usually, with the exceptions pond 3 and pond 4 where we did one-tail tests. But by and large, if our assumptions are met for the t-test, then our conclusions from a t-test will match the conclusions of a sign test. It's only when our assumptions are wrong, are not met, when we're non-normal, when our results might differ. Now, the sign test does have less power, so what happens if we get a p-value that's close? So we had one here, less than 0.08. Well, does this mean that there really is, the medians actually are equal, or did we lack the power to actually detect this difference? It's tough to say, but one thing we could do, if we have a question, is to generate bootstrapped confidence intervals. These bootstrapped confidence intervals are also a method that we can use to compare means and medians if some of our assumptions are violated. For the bootstrap confidence intervals, we're not going to compare medians, we're only going to compare means. So what is bootstrapping? Remember, bootstrapping is resampling with replacement. We use a sample function where we're going to sample a vector and we're going to sample with replacement. So each value has a chance of being drawn once, more than once, or not at all. When we generated a bootstrap confidence intervals, we had a script. We created our general R code where we had our vector, and then we created a blank vector to hold our randomized values. And then we have this for loop where we draw our sample with replacement of our vector, we calculate the mean, and then we saved the mean into this new randomized vector. And then we took the quantile of that vector. And normally we're working with 95% confidence intervals, so we want the 2.5 and the 97.5 quantiles. When we do this bootstrapping, we can make our comparisons based on whether or not our interval captures the hypothesized mean. If this interval captures the hypothesized mean, then we would say our sample mean equals that value. If the interval does not capture the hypothesized mean, then our sample mean does not equal that value. Another way to think about it is this. When we have our interval, this interval is not different, or the sample is not different than any value that is within that range. That also means that when we have our confidence interval, our sample mean will be different from all values that are not within that range. The only problem with this test, or with this method of assessing significance, is that there's no p-value associated with it. And some people can have a problem with it, with that. But it's perfectly legitimate. If all of our assumptions are met, this interpretation will hold true and match any conclusions from our t-tests. If our assumptions are not true, this method is a whole lot better than trying to run a t-test. So this would be our general code, where we copy and paste it, and we only replace this one line, for example, mosquito fish pond 1. And this would generate a bootstrap confidence interval. When I ran this, I got a confidence interval of 24.71 to 25.33. So what this tells me is that any hypothesized value that is within this range means that our sample mean is not different to those values. For our example, we were testing against 24.5. Note that the interval does not capture this hypothesized value. Therefore, we would conclude that our sample mean, that sample mean used to generate this value, this interval, is different from 24.5. Now, this is the long way. Let me introduce you to a function. So here's a bootstrap mean function. We create our function, much like we did with that standard error function. And I'm going to define an x, n, and ci for our confidence interval. First thing it's going to do is take our vector that we give it as part of x. We're going to strip out any missing data. Now this could be debatable whether or not we should include missing data. You can find arguments for and against. If you're curious about it, just look it up online. I'm going to just go ahead and remove missing data because it's usually unlikely that we have a large number of missing data from our data set. So what we'll then do is create our BS means vector. This will hold all of our bootstrapped means that we will calculate. And then we have our loop where we will generate a bootstrap sample and then calculate the mean and save that mean in our bootstrapped vectors. What we'll then do is take the quantile, but before we do the quantile, we're going to have to figure out what our lower and upper quantiles will be. So based on the 95% confidence interval, it'll automatically determine the lower and upper. So for 95, it's 2.5% and 97.5%. As part of the quantile function, this will output the actual 95% bootstrap confidence intervals. Now, as a note, when we have this function, we can change the number of replicates that we have, number of iterations. So you can change this number to 10,000 usually, but the default is 1,000. And the default here is 95% confidence intervals. But if you wanted a 90% or a 99% or maybe a 97.5% quantile, we can do it. We can do it. Also, this is the bootstrap mean function. If we wanted to generate a confidence interval of the median, we could. We just have to update our script, update our function so that we're calculating medians instead of means, or maybe variances or standard deviations, basically any value we want. I've just put this together because we're typically comparing means. How we use it is to get this into our R, run it so that the function is now available, and then we would use bs.mean. We'll give it our vector, whatever it is, probably data $ variable, and then leave the options as is, but normally increase their iterations to 10,000 and calculate 95% confidence interval. So let me bring over our studio. Up at the top, we have our libraries, our data, and now I've added a section for functions where I've copied and pasted the actual bs.mean function. Notice up in the environment, I have data and values, and when I run this, functions appear. bs.mean is now accessible. So let's do our bootstrap mean of pond1, or bootstrap confidence intervals. So this is pond1. What we would do is bs.mean mosquito fish $pond1. We want 10,000 iterations and we want a 95% confidence interval. When I run it, it outputs our confidence interval. So for a write-up, we would reference the interval and we were testing whether or not our mean was equal to a certain value, 24.5. So we would conclude the mean is not equal to 24.50 based on bootstrapped 95% CIs. And that would be sufficient. Alright, so you have the function. This function's also been posted on Blackboard. I've placed it as a .r file so you can open it up as a text and paste it into your useful function scripts. So what I'd like you to do is use that, generate confidence intervals, and have brief write-up that answers these questions. Now, we can do smaller and greater than for these. So pause the video, run your bootstrapping, and then we will discuss the results. So here's R. Pond2 is asking, is the mean equal to 25.15? I'll use bs.mean function to generate these confidence intervals, and I get this interval. I would conclude that the sample mean is equal to 25.15. Why? It's because 25.15 is captured by this interval. Remember, our sample mean will be equal to all values found in this interval. Since 25.15 is between these two numbers, we would conclude that our sample mean is equal to 25.15. What about Pond 3? Pond 3 asks, is the mean smaller than 25.05? Here's my script. 25.05 is captured by this interval. Therefore, we would conclude that the mean is equal to 25.05, which thus means that the mean is not smaller than 25.05 based on the confidence intervals. What about Pond 4? Is the mean greater than 23.75? Well, 23.75 falls below it. All of our bootstrapped means, or the collection of means, is above that 23.75. So the interval does not capture that hypothesized value. Therefore, we could say that the mean is greater than 23.75 based on the bootstrapped confidence intervals. So just as a review, we have the t-test and z-test. If we have a population standard deviation, or if we have to use the population standard deviation, we're going to perform a z-test. If we have a sample standard deviation, we're going to run a t-test. T-test has the assumption that our data are normally distributed. So before we can run our t-test, we have to assess normality. If our data are normal, then we can proceed with our t-test. But if the data are non-normal, then we should find an alternative method. If we're interested in comparing the means of these non-normal data, then we should use bootstrap 95% confidence intervals. If we're okay with comparing the medians, then we can perform the sign test. So that wraps up this presentation on one sample continuous data. What we will do now is take a brief break and get a summary of all of the tests that we've covered up to this point before moving on to analysis of variance.